Okay, so let's pull this open here. Let's picture. Perfect. MacBook Air, iPad, iPhone. I know, I am. Well, shizzle. Okay, you too could be. I'm just saying it's really not that pricey to be awesome. So if it doesn't come naturally, you just have to, you can buy it. I'm just saying this is my big advice for the whole quarter, really, for your life. And that one's free. It's like, okay. So there's MATLAB. So for those of you who have not used MATLAB, you're going to get awesome at it by the end of this quarter. Typically what happens, everybody has different levels of MATLAB skill walking into this classroom. And the first 2 weeks is a good equalizer because it just means that everybody starts working and you start loving MATLAB or something like that. Love might be a little bit of a strong word, granted, but anyway, let's kick some stuff around here. All right, so first of all, let's open a file, UM file. All right. What I always like to do in MATLAB is start all my code with those 3 commands. Clear all removes all variables from the, you know, one thing that people sometimes forget to do is clear all, and they get these results and go, how did that, because you might have been playing around with MATLAB for a couple hours, you have all these variables up on your desktop, and you forgot about it because you programmed it an hour ago, and then you think you did something, and it's actually, you were just filling in some things from a vector that you built a while ago, and you're going to get nonsense results. You know, when you run this thing with a clear all, it's like just eraser. You know you started clean. Close all shuts down all your figures. If you have a lot of data going to figures, that will greatly slow down your time. And CLC like wipes the screen clean. So this part here. Okay. By the way, can we get the lights down in the front? Awesome. Thank you. Okay. So there we go. Now, a couple things we're going to do. Let's start off with some things we're going to need. So first of all, I am going to do a shooting method, so I'm going to take off from one end and hit the target on the other end. I'm taking off from 0 and trying to land on 0. Now, I never really land on 0, so I have to pick a tolerance that I want to land on. So let's do the following. Just make something like this. There will be my tolerance. You know, as long as I'm within 10 to the minus 4 of my target, we'll call it good. You get to pick what that is. And in the homework, I'll tell you what you should set that to. Okay. So now let's think about what we want to do. Right behind that screen are the equations. Should have probably kept them on over here, but that's bad management skills. I just wanted to demonstrate for you what bad management skills look like. Totally on purpose. All right. So we had this equation, 2 equations, y1 prime equals y2 prime. Now, the way MATLAB works is here is how the function call goes to OD45, for instance. We're going to use OD45, which is 4th order Runge-Kutta. And let's talk about how you use this command. So first of all, you call right-hand side. Now, what the right-hand side is your function. It's your right-hand side function. In other words, that f. All MATLAB wants from you about that equation is what is that f? dy dt equals f. It's going to go in here. So let's call it f, right-hand side. And this is going to call a function called frhs.m. It's going to go right in here and say, let me go look for this function. It's going to be a .m file sitting in the same directory. And we'll build it in a moment. And it's going to say, there's my right-hand side file. This is the object which MATLAB is going to iterate on. How's it going to iterate? Well, I showed you what the 4th order Runge-Kutta thing looked like. It's just going to say, OK, there's the right-hand side. That's the thing I'm just doing, marching forward in time by doing an iteration. It's doing it for you. OK? There's the first thing in there. Second thing in there. You have to give it, what do you want to solve for? Normally you say, I want to solve for some x span. And by the way, what is our x span in this thing here? It just Negative 1 to 1. I'm going from negative 1 to 1. Start, end. Where I start, where I end it. That's it. Those two numbers mean that. Okay? So I put that in. Then, the other thing I need to do is tell it, well, what should it start from? I need an initial condition. Let's call this IC for initial condition. And what you have to specify are what are your initial values of y1 and y2. What do we know about y1 when we take off? What's the boundary condition? It's 0. Is that going to make sense? So I know what y1 is 0. What's y2? We don't know. We don't know. We have to guess, yeah. Let's guess A. And let's make A be something. Like, just make it 1 for now. We don't know what this equation is going to behave like, right? So right now we're just playing around, trying to build something and seeing what it looks like before we build our iteration routine or our shooting. And that's it. That is the basic structure. Now what it's going to give you back. You tell it the function to iterate on. You give it the time you want to solve it for or the span you want to solve for. You give it the initial conditions. Okay? There's some other things we could do here. But for right now, we're going to pass in some variables as well that live out here. And if we want to pass them in, I'll show you how to do that. But this will go and iterate for us. And what's it going to give back? It's going to give it back two things. Ty. T is going to be a vector. Okay? T is a vector that tells us all the times that we have solved from between negative 1 and 1. So the first value of t is negative 1. And it's going to take certain steps, dt, right? Remember how we marched forward with a delta t? And in fact, our accuracy of the scheme depends upon delta t. Well, it's going to give us, okay, maybe you stepped at negative 1 and then negative 0.9 and negative 0.8, blah, 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 all the way to 1. These are the actual points it actually stepped at. Y is the solution at time negative 1 all the way to 1. Each row is the slice of time, or a slice of x. And this here has two columns. Column 1 is y1. Column 2 is y2 at the different times. So this is our solution vector at these times. Okay, we'll play around with it in a minute, show you what it looks like. But that's what we get out of this thing. Yeah? Good question. All right, so here's an assumption. You ready? I know it's going to hurt a little bit. MATLAB does not trust you to pick a DT. You are untrustworthy. You might make a mistake and do something stupid. So what MATLAB does is says, tell you what, we'll handle that one. What we'll do instead is we will pick the DT so that we'll give you an answer that's accurate to 10 to the minus 6 per step. Everything in MATLAB is built this way. Don't touch delta t. Let us do that. You're going to mess up. We'll give you an answer that's 10 to the minus 6 accurate. This is the default. Okay? You can change that. And in fact, you will change it in your homework. So let me just say here, the next lines is if you wanted to change tolerances, it would go in this slot right here. We're going to do that today, this morning. But you can make it more accurate, less accurate. You can mess around with the error you want out. So if you want 10 to the minus 8 solutions that are accurate to 10 to the minus 8, you can get that. It still won't let you pick DT. If you want to pick DT, it says write your own code. Okay? That's how this thing works. All right, I don't know if did that sting a little to say that you are untrustworthy. I hate to say that it's so early in the morning, but just the fact. Yeah.
That tolerance that you would put in there, that's not the global tolerance at the end point, where you can like how you
no, this is different. This is local. Every step you make, every step you take, 10 minus 6 will be watching you. Okay, yeah, but that's it. Just local steps. And then after that, you can send in parameters like, hey, you know what, there's that beta in there. So let's just send in beta. Actually, I want this. We get to pick a beta value. We send it in. So after the tolerance settings here, everything else you throw in can be just variables that get passed into that subroutine. Okay? You send in values. It takes a look at them and says, OK, you sent me a beta. I'll use that beta. Now, first, this pretty much, the nice thing about MATLAB is it's doing all the heavy lifting for you. Because now once you write this code, if you want to plot your solution, so remember I said y comes in 2 columns now. Column 1 is y1, column 2 is y2. And by the way, what is y1? It's psi. It's the thing you're trying to solve for. So at the end, I can just say, when I'm done with this, I just say plot t versus first column. And the way the data is always arranged, right, there's going to be rows, columns, rows, columns. And if I do comma 1, it says go to the first column. The colon means grab everything in the first column. So I'm going to plot the whole first column, which is just psi. This is the whole code from the outside. Okay? To some extent. We're going to build on this. But these are the key ideas. We still have to do this thing. Okay? So let's go build that right-hand side, which is actually pretty simple to do. Let's give this a better name. Autumn 11. 581. Sure. Does that sound good to you? That sounds good to me. All I know is I have a bunch of files in here called Untitled 1, Untitled 2, Untitled 3. And I lose track. At least there's a 581 in there and Autumn 11. There's a chance I actually might understand what this code was. At least what period of my life it was written in. All right. So let's go do that. Let's file, save. Save. Save as. And we'll call this Autumn 11 581.m. So we're going to save that. Save. Where? MATLAB, sure. Okay. All right, so now we're going to open a new file. New M file. This is going to be a function call. And what we're trying to generate is the right-hand side of that function. What is the dy dt equals? What's over there on the right? We're going to call that RHS, right-hand side. And this is called Autumn 11. What did I call it again? 581 RHS, right? I think that's what I did. So this here is the name of the file you gave it in the previous. This here is what you're returning to the main code. Right? So this is what it's going to iterate on. It's always going to evaluate that right-hand side, iterate. Evaluate, iterate, all the way through. Now what did I send in here? Well, first, my x values. Second, my initial condition. Third, dummy. I call that dummy because it's a placeholder. This is where I normally would send in tolerance settings, but you're not going to do anything with them. Okay? So don't give them a variable name. I call it dummy. You're not going to. It's a dummy variable. You're not going to do anything with it, but you have to have a placeholder for it. And then beta. By the way, the order you send these things in matters. However you sent them in from the outside is how they have to be received on the inside. If you start mixing them around, you're going to have problems. Okay? So just send in the orders correctly, you'll be good. All right. And then all we got to do with the right-hand side is build it. The right-hand side, it's a vector, 2 components. And by the way, if you come right back here, it's so clear to see that y1 prime is equal to y2. Do you remember that? I do. Okay. Sorry. 1 second here. Let me pull up my. I'm doing it all at once. Okay. So what I send in here, by the way. All right. So I send in my initial conditions. And by the way, my initial conditions. Let's do the following, just to make this a little more clear. Y1 is the first component of my initial condition, right? Y2 is the second component of that vector. Okay? So I sent in this IC, which had Y1 and Y2 initially, and here they are. And what I want to do is say, well, Y1 prime was equal to Y2. And then here, the semicolon indicates that there's a carriage return. There's 2 ways to do that. I could either do this, and then y2 prime is equal to, if you remember, it was, what was it? It was, beta minus 100 times y1. Beta minus 100 times y1. That's it. So you can either do it like that with a return, or you can do this. We just put a semicolon there, and that's like a return. So two components. y1 prime equals y2, y2 prime equals beta minus 100 y1.